Hello everyone, it's me, Billy Younger again for Physics Solutions. I am solving a problem where, unlike the Atwood machine, where it's always smart, of course, to break down the two hanging masses and do a separate free body diagram for each, this is a problem where you're going to be inclined to use the entire set of objects. So you'll have three objects, and you're going to treat them all as one big object, and you write F equals ma for that from that free body diagram. And then you're going to have to break it up into individual parts so you can find other parts of the question. So just to show you how you can use Newton's second law to attack an entire collection of bodies as if they're one big rigid thing, and then how you can break the individual parts apart and compute yet another free body diagram. I've set up another set of free body diagrams to determine some of the internal forces. So let's get started by me sharing my screen so you can see the actual problem. So here's the problem, and I'm going to give you right now some rough estimates of what these things mean, because a 40 Newton force, a lot of students when they first start physics don't really have a good feel for Newtons, but I tell you a 40 Newton force is really about 9 pounds. I think it's 8.991 or something like that, 8.996 or 8.995 something. Anyways, the main thing is 40 Newtons is about 9 pounds. So almost as heavy as 2 pounds, 2 bags of sugar, which are usually 5 pounds, I think. Anyways, also this 10 kilogram box, that 10 kilogram box actually has a weight in pounds of about 22 pounds. The 20 kilogram box has a weight in pounds of 44, and the 30 kilogram box has a weight in pounds of 66 pounds. So just to give you some rough estimates. So it says a 40 Newton force is applied to a horizontal rope tied to the 10 kilogram box below. Another horizontal rope is attached between the 10 kilogram box and the 20 kilogram box, and another between the 20 kilogram and the 30 kilogram box. Assuming there is no friction between the boxes and the surface on which they're sliding, what accelerations will they experience? So we're trying to figure out the accelerations. We're going to assume, of course, these individual ropes never become slack, nor do they stretch, so that they're all traveling with the same acceleration. And then B, what will each tension be? So we're going to try to find the internal forces, which are compared to when we treat the whole body as one big 60 kilogram thing. We're going to find this T1020 tension and this T2030 tension. And you can see the 40 Newton acting there. So now that we've got all the numbers down pat, you have some sense that the 40 Newtons is 9 pounds of force. The 10 kilograms is about 22 pounds in weight, the 20 is about 44, and the 30 is about 66 pounds. So let's kill that and show you my document cam. So now we'll go ahead and switch to the document cam. And what I'm first going to do is do a free body diagram for the one big object. So the one big object, I'll initially draw it. It's basically one big object that we're ignoring has parts, and its mass is 60.0 kilograms. It has a force of 40.0 newtons acting on it. So the free body diagram for that one is basically this. We got a positive x-axis that way, a positive y-axis that way. This is a 60.0 kilogram mass. We have acting on it a normal force. That's the surface, the force that the surface is applying to it. Notice the normal force is due to some object actually touching it. In this case, it'd be the floor or the tabletop, whatever this is sliding on. So that's our normal force. The other force acting on it that is related to something that we can see or sees that's actually touching it, and that's what we sort of use for our free body diagrams. Everything that applies a force to something has to be touching that thing except for gravity. So in this case, we're going to say this right here is the force of 40.0 newtons that's pulling it to the right. And then finally, I've covered everything that's actually touching the box now, but I've got one more force, and that's the force due to gravity, which we call its weight. So here's the force due to gravity called weight. And of course, weight is m times g. And of course, m times g means 60 kilograms times 9.8, which I think is 588. 60 times 9.8 is 588 newtons. Now this one has a summation of forces in the y direction, but it just tells us something that we've learned over and over again. The summation forces in the y direction equals mass times acceleration in the y direction. We're not expecting these crates, the system, to jump up and down and not have any velocity, in fact, in the y direction. So the acceleration is going to be 0 in that direction. And we just get that Fn minus 588 newtons is equal to 0, which tells us that the normal force is actually 588 newtons. That's not very helpful. That's always the case. The normal force is always the weight whenever it's sitting on a level surface. That's the first thing. And two, no forces are acting on it in the vertical direction. So if I had someone pushing this way downward a little bit on the box, that would actually add another component, and that would alter the normal force. If I had somebody pushing up this way on it, that would alter my normal force. Or if I had somebody pulling upward on it, that would alter the normal force. The pulling up on it and the pushing up on it would in fact cause the normal force to decrease, whereas the pushing down on it would cause the normal force to increase. So as long as you don't have things pushing in the vertical direction against it, and as long as it's sitting on a horizontal plane, then the normal force would just be equal to the weight. What we really want to do, though, is attack the x component of Newton's second law, and that says the summation of the forces in the x direction is equal to mass times acceleration in the x direction. That's really the only acceleration we're going to have. We're going to assume the strings connecting the individual parts of the object are in fact not going to get slack or stretched, so the accelerations will all be one and the same. In this case, we're even treating it as it's one big object, so it's definitely okay. So we see here the only force acting on it, since we don't have any friction, is just the 40 newtons. So we say 40.0 newtons. That's acting in the positive direction, as you can see from here. And that's the only force acting on it in the x direction. So that's got to be equal to 60.0 kilograms times A. So we see A is in fact going to be 40.0 newtons over 60.0 kilograms. And a Newton is a kilogram meter per second per second. So divide that by kilogram, you just get a meter per second per second. And I think you all can tell that this, in fact, is going to be 2/3, which is 0.66. Let's go ahead and use 4 sig figs. That'll be 6.7 meters per second every second. So that's the acceleration. And I've actually carried one extra sig fig there, so I'll underline it. That's our acceleration, level A. And that's the answer to part A. Part B was asking about the tensions. And this is where we actually have to draw a free body diagram for the individual objects. So I'm going to draw one for the 30 kilogram. We're not going to need one for the 10 kilogram. I'm going to draw it for the 30 kilogram. Let's say it's right here. This is the x-axis. This is the y-axis. And that dot represents the 30.0 kilogram object. Acting on this, of course, is a normal force, because that comes from the table or the surface that it's laying on. That's actually doing the touching. So I'm going to call that Fn30, meaning the normal force for the 30 kilogram thing. We're not going to worry about it. I think you can already guess the results. But one force that acts on things that doesn't actually cause it to touch, require it to touch the thing, is the weight. And that's what's going to be acting here. They should be, in fact, the same magnitude. So weight, which equals m times g, is just 30 times 9.8, which is 294 newtons. Now, that's the thing that doesn't touch it that causes a force. And there's one more thing that is touching it and therefore causes a force, and that's the tension in the string. And that tension in the string is called T20-30 or 20 minus 30, whatever you want to call it. So that's something we're actually trying to solve for. The summation of forces in the y direction is just going to give us Fn30 minus 294 is equal to 0, again, because it's not accelerating vertically. But the summation of forces in the x direction, that's helpful. So the summation forces in the x direction equals m times a, and a is the only acceleration, so I need not subscript it. And I'll get T20-30. That's the only force, and it's positive, acting in the positive direction, so I'll leave it as positive. That's equal to 30.0 kilograms times the acceleration, which we found was 0.6667 meters per second every second. And that gives us a result of, I'll just move the paper up a little bit. That gives us a result of 60, or excuse me, 30 times 6 or 0.666. So 30 times 0.6667. That gives me 20.00 newtons is equal to T20-30. Okay. Notice physically, that's exactly what we expect. We expect the tension, since that's the only force really trying to pull this block or this box, we expect that tension to be exactly the force needed to accelerate 30 kilogram object. That's 0.6667 meters per second. And that's exactly what we got, 30 kilograms times 0.6667. Now we do the same thing for the 20 kilogram box. And I'm going to say it goes right here to here. And this is my x-axis and this is my y-axis. And this dot represents my 20.0 kilogram block or box. I know I keep using those interchangeably. It has a normal force acting on it, of course. That normal force we'll call FN20, say. It has a string tension pointing to the right, and that's the tension that we call T1020. So this is T10-20. That's the one that comes off the 10 kilogram block and then attaches to the 20 kilogram block and is pulling the 20 kilogram block. But there's also another rope attached to it, and that rope is off the backside. So that points this way. In fact, the 20 kilogram box feels like something's slowing it down. And it's this tension back here, which is called T20-30. And those are all the objects that are touching it. This is the surface that it's sitting on, is touching it. This is the string to the right that's touching it. This is the string to the left that's touching it. So we've gotten everything that's touching it. The only thing we haven't gotten is the one thing that causes a force that doesn't touch it, and that's gravity, which again, we say results in weight. Weight in this case is equal to M times G, as it always is. But in this case, it's 20 kilograms instead of 30 kilograms, and that's 196 newtons. Again, FN20 is going to be equal to 196 newtons, as we expect, but the summation of forces in the y direction or in the x direction is relevant. So the summation of forces in the x direction equals MA. I'm going to try to not force everything in such a small space. So I see the positive force is T1020. So I'll say T10-20 minus T20-30, which we found was in fact 20 newtons. That's the total forces acting in the x direction. And that's got to equal 20.0 kilograms times 0.6667. So I know I didn't fit in the units there, so I'm going to come down here and write T10-20 is equal to, if I add 20 to both sides, I'm going to get 20.00 newtons plus 20.0 kilograms. Here's where I can show you what turned out to be too tight to fit in there, times 0.6667 meters per second every second. So this is going to give us, in fact, 20 newtons plus 20 kilograms times 0.667. And that figure is 13.33 kilograms times a meter per second is in fact a Newton. So we get that this force is going to be T10-20 is actually equal to 33.33, carrying one extra sig fig, newtons. And that's part B. Now this you should expect, because really what we're looking at, remember, is a 10 kilogram block. There's the 10 attached to a 20 kilogram block attached to a 30 kilogram block, and then a force pulling it this way. That force is only 40 newtons. So that force actually has to pull the total mass of 60. And if you take 60 and divide it into 40, you're going to get 0.666. Like we did, that's the acceleration of these objects. But when you look at it, this tension has to pull only 50 kilograms. So that tension is obviously going to be a little bit less than the 40. In fact, it turns out to be 33.33. But this tension pulls even less. It only has to pull the 30 kilograms. And that one, of course, turned out to be 20.00 newtons. So that's it. That's how you solve that problem. Notice how we could actually, in some cases, treat a collection of objects as one big object, as long as we don't need to know the internal forces, like the forces between the individual parts, because we can't use it for that. Then we can do the free body diagrams for the individual parts, and that will allow us to determine the internal forces. So that is a skill that you need to know, but it's very seldom that we do it where you do the whole system as one object. Do not, I promise, do not try that with an Atwood machine or a half an Atwood machine. Those types of problems, you tend to make mistakes when you're trying to do it. So it's not that you can't, it's just that it's really hard to think your way through it. So we'll call that an end. I'm going to turn the camera back to me and tell everyone have a good day. I hope that was helpful. Bye-bye.